Now let's look into fundamental side of Raoult's law. As we saw, it's a liquid and liquid and both of them are volatile. And vapor pressure, okay, let me clarify that. Vapor pressure is the pressure exerted by vapor on the surface of a liquid. So imagine a lake is there, okay, there is a lake or even a bowl of water. The amount of pressure that the surface feels, okay, amount of pressure by the vapor is called a vapor pressure, okay. The best way to see it is, you can imagine that the vapor pressure is with which the vapor can go out. The lower the vapor pressure, meaning it can easily go out to the vapor phase. So the lower the vapor pressure, okay, it can easily go into vapor phase. So any time you have a lower vapor pressure, that particular liquid loves to be in the gas form. So when you have a two liquid system, chi A, chi B, let's say for example, this is chi A, this is chi B. Here when you look at the graph, they are all the same, just not drawn to scale, they assume that they are all the same. My B has a lower vapor pressure compared to A, okay, this is solution. So if you take for example a sealed system, I have sealed all of them actually, some graphs actually do not put the line, it has to be sealed. Now you take, let's say for example, half a bottle of water covered, okay, when you look at it, for example, alright, let's look into this. This is water, I am not marketing Pepsi here, so this is just plain water, it has its own vapor pressure. So now let's say this is a two component system, okay, there is water vapor, water here and obviously water vapor and also oxygen. Now in the liquid, compare the both of them, water vapor versus oxygen, who loves to be in the gas phase? Oxygen. So the mole fraction of oxygen is high in the gas phase, mole fraction of water is high in the liquid phase, that is you want to remember. So let us assume that A is water, B is oxygen. Chi A is higher for water, chi B is lower for oxygen. Conversely, the mole fraction in the gas phase Y, okay, Y of A will be lower, okay, Y of B will be higher. So Y of B will be higher because what's low in the liquid system will be high in the gas system, you want to remember that. Alright, so now I have this, so I start with a pure solvent, so the pressure here is only because of A, so its pressure total equals P naught A. Here only B, pure B, so pressure is only because of B. Okay, so chi of A here is 1 because I do not have any B, mole fraction is 1. Here I do not have any A, so chi of B is 1 or chi of A is 0, chi of B is 0, B is 0, straightforward. Okay. Anywhere along I have a mixture, these are pure solvents, anywhere along I have a mixture. This particular line shows the mole fraction of A dependence. So now if you see pressure, okay, because of B, pressure because of B is nothing but your P naught B times chi B, Raoult's law. This is A, P naught A times chi A, that is Raoult's law, okay, straightforward. This is an ideal system. So the first graph is ideal, A and B behave ideally. So the vapor pressure at any time, this line equals PA plus PB, and we just saw PA can be written as P naught A chi A plus P naught B chi B, we saw the derivation itself. So this is behaving Raoult's law, okay. An ideal solution has three conditions, and this has come as one of the NEET question itself. Which among the following is not a property of an ideal solution? Condition number 1, it has to obey, an ideal solution has to obey Raoult's law at all conditions, okay. It has to obey Raoult's law at all conditions, it has to follow this graph, this line. So now if you take for example any particular system, for example this point, okay, let us call this x. At this point x, this is the line of A, so this is PA at x, this is PB at x, okay. So now take this plus this, so basically imagine this, that is about till the cap's height, okay. This is about something here, correct. So I am going to be adding, let us say for example I am measuring this somewhere here. So I have distance here, that is the length of that, and the length of this is somewhere till here. So, I am going to add the length of here. So, this is this plus this PA plus PB. So, this is the total height, okay. That is about this plus this cap, right. Alright, this is what you have. If you add this here, if you drawn this to scale, it will add up and it will be exactly this height. So, at any given point, at this point for example, at this point, this plus this will be this, okay. This is Raoult's law. So, ideal solution has to behave Raoult's law, obey Raoult's law at all conditions. Now, A and B interactions, okay. When I have pure A, I have AA interaction. When I have pure B, I have BB interaction, okay. A Raoult's law obeying solution, ideal solution will have AB interaction, okay. Two different solvents interacting will be same as the interaction between AA and BB, okay. How you want to see it is, let us say for example, I have A and I have B, I mix them together, meaning A and A have been interacting, I break that, B and B interacting, I break that, okay. That is endothermic process, and then I form AB, exothermic process. So, the sum total of all this energy is 0. So, AA interaction and BB interaction is equal to AB interaction. So, the sum total of all this is 0. So, delta H change in enthalpy is 0. If AA and BB interact the exact same as A and B together, meaning 1 liter of A plus 1 liter of B will give you 2 liters of AB. So, they will have the same volume. So, change in volume is 0. Now, because you are mixing it, they give a symbol, delta H of mixing is 0, delta V of mixing is 0. These are the conditions for Raoult's law, sorry, ideal solution. Obey Raoult's law at all condition, delta H of mixing is 0, delta V of mixing is 0, right. Now, what if the solutions do not behave well, okay. What if they do not behave ideally? What they can do is, they may love each other more, okay. They may love each other more means they will come closer together, okay. If they love more, for example, A wants to go into vapor, B wants to go into vapor, okay, at their own rate. But what if they love more, meaning A is not going to let B go up, B is not going to let A go up, okay. In that case, it sounds like both of them do not want to go up. So, both their vapor pressure decreases, okay. This will be the vapor pressure of B. It has decreased compared to what it used to be. This is vapor pressure of A. This is decreased compared to what it used to be, okay. Now, what will be the sum total of when I mix the mixtures? So, it will also follow the same pattern. Now, this is what is called negative deviation of Raoult's law. Vapor pressure of the mixture goes down compared to ideal solution. So, now what has happened here is, does not behave Raoult's law, okay. It does not behave Raoult's law. Second thing is AB interaction versus AA-BB interaction. So, AA and BB used to interact, but I just told you A and B interact even better. So, AB interaction is greater. So, if they interact more, okay, if they interact more, meaning AA interaction is weaker, BB interaction is weaker. So, I need to break these interactions and form this interaction. So, breaking is endothermic, bond forming is exothermic, or interaction is exothermic. So, the amount of energy I need to put to break this is lower than the amount of energy that is given out. So, this is going to be an exothermic process. So, delta H of mixing is negative, okay, because I break weaker bonds, I form stronger bond. Now, they are going to interact much better, means I can pack them much more. So, 1 liter plus 1 liter is not 2 liters anymore, it is less than 2 liters. So, delta V of mixing, the change in mixing is negative, it has gone down. This is negative deviation. The negative deviation is not because of these negatives, it is coincidence, it is easy for you to remember. Negative deviation means the vapor pressure is lower than expected. This is Raoult's law. The black line is Raoult's law, okay, behaving like an ideal solution. The blue line is what is actually it is doing. The last one is just the opposite of negative deviation, positive deviation. Vapor pressure of the mixture is high compared to an ideal solution. What it means is A and B are happy with each other. When I mix them, they don't like each other. Okay, if you don't like the other gas, obviously you don't want to be together in the liquid phase, you want to go to the vapor phase. You will easily go. So what happens to your vapor pressure? Goes up. Your vapor pressure goes up. Similarly, the other person also doesn't want to be with you. The vapor pressure also goes up. As a result, the vapor pressure of the mixture is higher than what Raoult's law predicts. So it doesn't obey Raoult's law. AB interaction, the interaction between you and the other one is not as great as AA and BB, because I have to break stronger bonds. I have to put in more energy, and I don't get all of it back because I form weaker interactions. So I put more, I gain only very less outside. So the entire process is endothermic. Delta H of mixing is positive, and delta V of mixing, because they don't like each other in the liquid phase, 1 liter plus 1 liter will stay far away. It will become not equal to 2 liters, it will become more than 2 liters. So delta V of mixing is positive. Okay. There is a list of examples that are following this pattern. They can actually ask you that. In general, ideal solutions are things that are very close in nature, okay, very close to each other in molar mass, the shape and the fundamental functional groups as well. For example, benzene, toluene, they are much closer, okay, hexane, heptane, pentane, hexane, okay, these are going to be ideal solutions, okay, very close to each other. For example, you can take any given organic compound, its homolog plus CH2 will give you the same ideal solution. Negative deviation is when their interaction is much stronger, okay, so the vapor pressure goes down. The best example is water with any of the acid HCl or HNO3 or even acetic acid. What happens is you break the weaker hydrogen bonding and you form stronger hydrogen bonding. So water with acids are going to be negative deviation of Raoult's law. Positive deviation is when you are mixing two things that don't like each other, okay, so meaning different type of functional groups. Example, acetone, ethanol. Acetone is happy by itself mixing with acetones. Ethanol is happy having its own hydrogen bonding with other ethanol molecules and happy. So when you mix acetone and ethanol, okay, they don't form efficient hydrogen bonding, so they don't like each other. So the vapor pressure of such a system is positive. Okay. The important thing that I want to say, the normal correlation of Raoult's law that you are going to see is in boiling point. It's exact opposite of vapor pressure. Vapor pressure is how easy a given system can go into vapor. Boiling point is opposite. Higher the boiling point, meaning I have to put lot of energy to make it go into vapor. So higher the vapor pressure, lower the boiling point. Negative deviation of Raoult's law in vapor pressure is positive deviation in boiling point, meaning such a system interact much better, so boiling point has gone up. All your acid and water will be higher. Similarly, the positive deviation in vapor pressure of Raoult's law is going to be negative deviation in boiling point. They are not going to interact very well, so I don't have to put in a lot of energy, it will easily go away. This is the fundamental behind Raoult's law. You need to be able to understand it, and the most important question that has come few times is, what are the conditions for Raoult's ideal solution, or which is not a condition for ideal solution? Remember these three, okay, that one. Second thing is deviations. The last small bit that you are going to have here is azeotrope. Okay, this is called zeotrope. Ideal solution. Azeotrope is opposite, as the name says. What happens with an azeotrope is, see, when you see this negative deviation, you see the blue line. The blue line is lower than the black line, but no point in the blue line is below P naught B or above P naught A. Same here. Okay, maybe I have drawn this way. So this is P naught A. The blue line traces between P naught B and P naught A. The blue line traces between P naught B and P naught A. Sometimes you form mixtures such that the interaction is much stronger. Okay, they interact strong. For clarity, I am going to erase these as well. Okay, they interact strong such that their mixture is actually, some part of it is outside the region. Okay, this is called azeotrope. These are also called constant boiling mixtures. Okay, meaning the mixture boils in such a way that the constitution of the liquid, whatever mole ratio they are in, okay, the same mole ratio they will go up. Okay, 30% A for 70% B, the same way they will go up. What it does is it gives you a problem in fractional distillation. I can use temperature and play with the boiling point and separate A and B, but not in terms of azeotrope. For example, if I take this position, okay, B is higher in boiling point because lower in vapor pressure. Okay, so it's higher in boiling point. So slowly, if I heat, only A should come out, but the certain percentage mixture of A and B, not at this point, around this region where it is below that. In this region, what happens is, in that concentration you have, let's say for example 30-70, something like this. If you take it, you slowly increase the temperature, neither A nor B will distill out, they will come together. Constant boiling mixture, so I cannot separate them. That's all you have to know. This is called, vapor pressure wise, this is lower vapor pressure, correct? Negatively, lower vapor pressure. What happens in boiling point? If this is boiling point, it will be opposite. Okay, boiling point will be, I cannot draw it, it has to be this way. Maybe I will draw it here really fast. The boiling point graph, okay, this is chi A, chi B. Instead of vapor pressure, I am going to plot boiling point. This will be boiling point of A, this will be boiling point of B, opposite of the vapor pressure. This is what is ideal system. This actually will follow a different trend. Okay, somewhere here, up to here, it's easy, they follow. But above here, particularly this region, they are constant boiling liquids. Okay, so the boiling point of the mixture is higher. So these are called high boiling or high boiling point azeotropes. Similarly, here if I do, I'm just going to have, I'm going to superimpose on this graph itself. If you see, the vapor pressure is higher than pure A and pure B. Okay, that's something you want to know. Here the vapor pressure is lower than pure A and pure B. Boiling point is higher than pure A and pure B. Here the vapor pressure is higher than pure A and pure B. Boiling point is lower than pure A and pure B. For example, for that it would be, so this is high boiling, this is low boiling azeotrope. Okay. This is the normal graph you see. These are constant boiling mixtures, that name you want to remember. They cannot be separated by fractional distillation. There are other ways to do. Okay, and also they actually have the same type of constitution in the liquid phase and vapor phase, that you want to remember, and you want to know that this boiling point graph is opposite of vapor pressure graph. Okay. Now the best example of a high boiling azeotrope is water and acid, HNO3. Now let's take HCl. HCl is a gas, water is 100 degrees Celsius, but aqueous solution of HCl at certain concentrations boils at a temperature higher than 100, higher than the gas, higher than the liquid aqueous solution itself. That's called a high boiling azeotrope. Alright, this is the fundamental behind Raoult's law. If Raoult's law comes, I can guarantee you it is going to revolve around what I have been teaching in the last few minutes. But understanding is different though. I can confuse it because it's a theoretical question. You need to be very clear in the terminologies. Vapor pressure is opposite of boiling point. Okay, take a minute, read the question again, statement question, because easy 4 points can become -1. Your job is to make sure that you get the -1s converted to +4. Okay, thank you guys.